I'm going to work some problems here to review for the Chapter 4 test. So first we're going to graph y equals 2 times 0.6 to the x. So hopefully we recognize that because the base is less than 1, this is going to be a decay function, and that when x is 0, 0.6 to the 0 is 1, and the 2 is going to be a vertical stretch. So in particular, this curve will go through the point 0,2. It will still have a horizontal asymptote at y equals 0, and because it's a decay, it's going to fall from left to right. So the three things that I'm looking for is, can you correctly figure out where this point goes? Can you get the right shape of the curve? And can you label the asymptote correctly? So let's take a look at the next one. Y equals 3 times 2 to the x. Because the base is bigger than 1, it's going to be exponential growth. And the 3 is going to mean it's going to cross the y-axis here at 0, 3. The asymptote is still going to be the x-axis, y equals 0. And it's going to be growth, so it's going to rise from left to right. On the next problem, we're going to solve this. So first we're going to write everything as powers of 3. So the 3 is already written as a power of 3, 3 to the x squared. The 9 is 3 squared, which is going to in turn get raised to the x. And the 27 is 3 to the third. So this becomes 3 to the x squared. And when you raise a power to a power, that's going to make that 3 to the 2x. Now, when you have two powers with the same base that are being divided, we subtract the exponents. So that's going to be 3 to the x squared minus 2x power equals 3 to the third. Once we get two powers with the same base equal to each other, that means we can drop the bases and set the exponents equal to each other. Now we've made it into an ordinary quadratic, so we can subtract that 3 over to make it equal to 0, factor it into x minus 3x plus 1, and solve it and get 3 and negative 1. For the next one, resist trying to distribute that negative 1 exponent. That is not a legal mathematical move. Instead, we will say 3 to the negative 1 is 1/3. 3 to the negative 2 is 1 over 3 squared. We will still resist the temptation to distribute that negative 1 exponent, which would be incorrect. We'll get a common denominator for our fractions and get 3/9 minus 1/9, which is going to be 2/9 to the negative 1 power. Now that we have a single fraction raised to the negative 1 power, we can take its reciprocal. On the 16 times x to the negative 2, all raised to the negative 3/4. Now when two things are being multiplied and raised to a power, they can each get raised to that power. So I'll come back to the 16 to the negative 3/4. When you raise a power to a power, we're going to multiply the exponents. So the negative times negative is positive, and we're going to end up with a 9 in the exponent. Now the 16 is 2 to the 4th raised to the negative 3/4 power. We can again cancel those 4's, get 2 to the negative 3, which is 1 over 2 to the third, and so we will get 1/8 x to the 9th, or you could also call that x to the 9th over 8. Either of those would be acceptable. For the next one, we're going to write everything as a power of 2. So this is going to be 2 to the third raised to the negative 2, because 8 is 2 to the third. 4 is 2 to the second. 32 is actually 2 to the fifth. So that's going to become, when you raise a power to a power, we'll multiply those exponents and get 2 to the negative 6 times 2 to the second, and then we're going to get 2 to the negative 5 in the denominator. Multiplying 2 to the 6 times 2 to the second will add exponents and get 2 to the negative 4. When we have division of two powers with the same base, we will subtract the exponents, and negative 4 minus negative 5 is going to be a positive 1, and so we'll get 2. Let's go to the next panel. So here we're going to use our properties of exponents. B to the n plus 1 times b to the n minus 3. We'll add those exponents. The n plus n will become 2n. 1 plus negative 3 will be negative 2. And in the denominator, b to the n to the second will multiply those exponents and get b to the 2n. Now we can subtract exponents because we have division by two powers of the same base. And if we subtract off the two n's, we're going to get b to the negative 2, which would be fine. Or you could also call that 1 over b to the second. Either of those would work. So with the next problem, w of t equals 25 times 1.027 to the t gives the wages for a job in thousands, t years after 2005. So what is the interpretation of W inverse of 30? So the original function W of t inputs a time in years and outputs a wages given in thousands. So what the inverse is going to input is our wages in thousands, and it will output a time in years. So the interpretation of W inverse of 30 is that it will be the number of years until, so it's going to be that time value, the number of years it will take for this wage earner to earn $30,000 in a year, for his wages to reach $30,000. Now, to find W inverse of 30, what we're going to do is take the 30 as, which is an input value for the inverse, which means it'll be an output value for the W of t. So we are going to get to this, is what we're looking at. And now we can, if you like, graph that and find the point of intersection. That's perfectly okay. If you want a preview of what we're going to do, because we haven't really talked about logarithms yet, although you have done this in your Algebra 2 days. So I'm going to work it as logarithms, even though you can just graph it on the test. But we can get a chance to kind of preview where we're headed with this. So I'm going to divide the 25 over. You don't have to, but you can reduce that. So 5 goes into 36 times and into 25. It's going to go on to our calculator in a moment anyway. Then we can take the log of both sides. So that's the log of 6/5 will be the log of 1.027 to the t. We can use our properties of logarithms, if you recall, and move that t out in front. So we get log of 6/5 is t times the log of 1.027. Then we can divide to get the t by itself and get the log of 6/5 over the log of 1.027. I'm going to throw this on my calculator and get it to 3 decimal places. And if you graphed it, we should still get the same answer. I'm going to pause this for a moment until I can use my calculator. So I'm getting 6.843 years. On to the next one. Write an equation for the rabbit population in Laramie, t years after 2010. If there were 5,000 rabbits in the year 2010, and A, the population was growing by 250 rabbits per year. So if it's growing by a constant rate, that's a constant rate of change, that's going to be linear. And so, I'm going to say that the population of rabbits, P of t, is the 5,000 that we started with plus 250 times t. So that's going to be linear. And part B, it's increasing by 5% per year. So increasing at a constant percent is going to make it be exponential. So we'll have 5,000, and that will be 1 plus r, which is 1.05 to the t. And part C is saying the population is growing at a continuous rate. That means we're going to use Euler's number E. So it's going to still be 5,000 for the initial value. And now we're going to have E raised to the, and the R becomes 0.04 t. Excuse me. Let's go to the next panel. And now we're going to see that sales are going to increase by 6% per year for 8 years. By what percent did the sales increase over that time? So the amount that we have, I'm going to change my color there. I'm going to go with maybe a green. So the increase by 6%, so our A is going to be the initial value, which we don't, initial amount of sales, times 1.06, there's our 1 plus r, for 8 years is to the 8th power. And we want to know what did that increase by over that 8 years. So we want to know what is that value right there, 1.06 to the 8, and then we're going to set that equal to 1 plus r. So 1.06 to the 8, as I put that into my calculator, looks like 1 point, and I'm going to go 5 places, 59385, 59385, and then I rounded that to the 5, that last 5. Now that is going to be the 1 plus r, where r is the percent that it increased over that entire time. That is, we multiplied our original value p by that 1.59385, knowing that that holds in it the 1 plus r. So that means we're getting that if we subtract off the 1, we get 0.59385. So that means this increased by 59.385% over that 8-year period. Notice that's significantly more than just taking 6 times 8, which would have implied that we would have gotten a 48% increase. But that's the power of the compounding. Looking at the next one, a prairie dog population decreased by 12% each year for the last 5 years. By what percent did the population decrease over that time? So this is a similar problem, only now we're talking decrease. So the amount is going to be P times, I'm going to still call this, since it's decreasing by 12%, I'm going to call that 1 minus 0.12 and raise that to the 5th power. So I'm going to clean that up a little bit and say 1 minus 0.12 is going to be 0.88 to the 5th power. So now we're interested in what is that 0.88 to the 5th, because that is going to hold in it our percent decrease. So putting 0.88 to the 5th power in my calculator, I'm getting 0.52773. 52773. So that is, again, that 1 plus r for that 5-year time period. So subtracting that 1 from the answer we got is going to give us, so before I make it a percent, it's going to be a negative 0.4722. I'm going to round that to 7. And so that means that it decreased by a negative, or it decreased by 47.227%, or we could say it decreased by a 42.227%. Don't say decreased by a negative. Okay, Break Your Leg Loan Company charges 1.2% interest per week. I think the name of that comes from how they get their money back. What is the effective annual interest rate? So we're asking for how much is that interest is it being charged in a year. So we are looking for then this in our formula, A equals P times 1 plus R over N to the NT. Well, we already have that this is our weekly interest. So this is going to be then 1 plus the 0.012. That's going to be how much interest is charged each week. And in the course of a year, there are 52 weeks in a year, so we are going to raise that to the 52 power. And our answer is going to give us a 1 plus R, where that R is going to be the percent that was charged over the course of that year. So 1.012 raised to the 52, I'm getting 1.85994, and then I'll round to 6. So if we subtract off our R, that's telling us that we actually were charged 85.946% in a year. Not a very good deal there. You want to pay that one off quick. Now the yellow one, a new boat cost $30,000 in 2015. By 2018, it had depreciated, that is declined in value, to $16,000. We want to find an equation for the value of the car T years after the purchase if the depreciation is linear and then exponential. So what we're getting is a couple of ordered pairs here. So we know our time 0 is going to be in 2015. So that means at time 0, that value was 30,000, and it looks like in 2018 was 3 years later, the value was down to 16,000. So if it's linear, our rate of change, our slope, is going to be the 16,000 minus the 30,000 all over 3 minus 0. So that's going to be, I think, a negative 14,000 over 3. That's not going to come out very pretty, so I'm just going to leave it like that for now. And we know that since we are given the value at time 0, that's actually our y-intercept. So we can say that y is equal to a negative 14,000 over 3, and x or t, I'll go with x, and then plus the 30,000 was the value at time 0. So there's our linear model. Now the exponential model, we're going to assume that this is y equals ab to the x. Again, since when x is 0, we're going to get 30,000. So that means 30,000 equals a times b to the 0. So that tells us that a is 30,000. So then we can say that the 16,000 is going to be a, which is 30,000, times b to the, and that'll be the third power. So we can divide by the 30,000. So I'm going to call that 16 over 30 and just cancel out those zeros. Those 3 zeros is b to the third. And we will take our 16, what did I say, 30th. Let me write a better 30th there. 16, trying to get my pen back, 30th to the 1/3 power. Let me do that. 16 divided by 30 raised to the 1 divided by 3 power, and we're getting 0.811 if we round to 3 decimal places. So that's going to make our equation be y equals, I don't know if I can squeeze it in here, 30,000 times 0.811 to the x. Whew. All right, let's see what we got on the middle. So here we have an investment increases in value by 40% in 7 years. What is the effective annual rate? So we're going to say A is equal to, we don't know what we started with, and it's going to be 1 plus, we're just going to leave it as R, so effective annual rate means it's going to be compounded once a year. That's to the 7. Let's see, if it increased in value by 40%, P was our initial value, so if it was 40% bigger, that means it's 140% or 1.4 times what it was originally. So we're going to try to solve this for the R. So it turns out that it doesn't really matter what we started with because that's going to divide out. So we'll get 1.4 is equal to 1 plus R to the 7th. So we will raise both sides to the 1/7 power. And so if I put in 1.4 raised to the 1 divided by 7 power on my calculator, I'm getting 1.04924 is our 1 plus R. And so our R is going to be 0.04924 as a decimal. We want it as a percent. So our effective annual rate is 4.924%. So in order to increase by 40% in those 7 years, it was increasing by 4.924% each year. Now the next one, this one, there's not really any great way to do this except by using your graphing calculator and graphing it and finding that point of intersection. And I think there's actually going to be 2 of them. So we're going to put those into our calculator, y1, y2, and we're going to graph that thing. And we should be getting the exponential is going to look something like that. And the straight line is going to look, I think, something like that, roughly. And so we're looking for what are those 2 x values that come from those points of intersection. So I'm going to pause this and do it myself, and then you can do the same, and we'll compare our answers. So the points I got were x equals negative 1.553. So that's going to be that point right there. And then x equals 4.117, which is going to be the x value that comes from there. So we're solving this equation with x's in it, so our answers are going to be x's, not ordered pairs. If we'd been asked to find the points of intersection, then we'd have had to have given our answers as ordered pairs. Okay.